In this video, we will solve problems dealing with mechanical properties of materials. In the first problem, we have a circular bar of magnesium 750 millimeter long, and it is loaded in tension so that an elongation of 6 millimeter is reached, and then the load is removed. Material stress-strain curve is given. What is the permanent set of the bar after unloading? Well, they are asking the new length. What is the new proportional limit? Here you have the loading. We start at point O, apply a load, go through the yield point, reach point B, and at this point there is a total strain epsilon B, which corresponds to 6 millimeters. Okay, then the next step is we unload the specimen or the bar. Well, this part is regained, and here we have a permanent deformation, epsilon permanent, and this is how the problem looks like. The first, we calculate the stress and strain at this point P. We know that the deformation is 6 millimeters. The initial length was 750. The calculation gives me 8 times 10 to the 3. So that is, in the diagram, it is something like this. So when you go up, your sigma is there 180 megapascals. So we have the epsilon and the sigma in point B. Next, we unload, where from here we begin unloading. We unload, and when we unload, this curve must be parallel to this. So I need the elastic deformation. But, well, as you see, nothing is given, so I have to calculate the elastic deformation on my own. So I know this slope. Let's take this point and this point, and so I use this triangle. So this part is 178, and this one is 0.04. So the calculation gives me that the slope is how much? 4.45 10 to the 4 megapascals. Okay, this is the result. So I know my A value, so I need to calculate this value. In order to find this value, what I have to do is, over here, the Hooke's law is valid. Sigma equals E times epsilon. Epsilon equals E is sigma over E. Sigma over E. I know it's 180. This is what I have calculated. This is my epsilon E. What is epsilon E? Epsilon E is this value. This value over here, which is release under unloading. Next step is to find the residual, this part. So what should I do? This is my total. This is the elastic portion, which is release 8 minus this, gives you the residual strain. The question is the permanent set. That means how much longer is the new bar. So what I do is, the initial length was 700. That is the residual remaining strain on the bar. So the bar is 2.97 millimeter longer. That's the permanent set. Question 2, what is the new proportional limit? So we know that when you load and unload, every loading and unloading, when you start loading from here, will follow the slope in the beginning, so your proportional limit when reloaded will remain 180. A brass specimen, maybe in a tensile test, is actually loaded. Diameter 10 millimeter, gauge length where we do our measurements is 50 millimeter. When the tensile load reaches a value of 20 kilonewton, the distance between the gauge marks are increased by 0.122, so it becomes that much. Calculate the elastic modulus of the brass, and if the diameter decreases by 0.0083, find the Poisson's ratio. Very simple problem. These are the values given: force, the elongation, and the decrease in the diameter. First, find the stress. This is my force, and the diameter is 10 millimeter, the area, and if you do the calculation and the unit conversion, then your stress is 254. Next, for this load, I have an elongation of 0.122. This is the initial length, and so the strain is also very easy to find. Next step is we assume that the Hooke's law is valid. What does it mean? So we are in this region, in the elastic region. Here, the elastic modulus is sigma over epsilon. These values are put here, and the modulus of elasticity is 104 gigapascals. Next question, Poisson's ratio. We know that the lateral displacement delta D over D is epsilon prime, and epsilon prime, that's the lateral displacement to the longitudinal strain, gives you the Poisson's ratio with a negative. So this value is delta D over D. We put in the values and find that 0.34, which is a typical value for metallic material, is obtained. Next question. Steel bar, length 2 meters, stress strain diagram. You see here elastic and no strain hardening, it goes parallel. So when you reach this point, 250, then the elongation or the deformation continues. Well, the yield is 250. Modulus of elasticity is the slope is 200. The bar is loaded until an elongation of 6.5 millimeter is reached and then unloaded. Calculate the final length of the bar. You see, during unloading, some part of the strain is released, then we will have a final length. First, apply, reach 250 and move to point B and reach this epsilon B. Epsilon B corresponds to 6.5 millimeters. Length, yield strength, elastic modulus, and the delta. For point B, for this point, the stress is very obvious. It is always 250. The material is not strain hardening, and the strain delta is 65, L is 200, 00325, 00325, somewhere here. Point B is somewhere here. Okay. Then we have to unload like this. When you unload, you will get an elastic part which is released. Now, the elastic recovery for unloading is this recovery, that is 200 divided by 20. You know, this curve is sigma equals E times epsilon, and epsilon is sigma over E. Sigma is 250 this point. E is the elastic modulus, is given as 200, and this elastic recovered strain is 0.00125. Okay, the total was something like this. So the residual is this minus this. It is 0.002 is the residual strain. The final length, well, we know the initial length. The initial length was 2 meters. So the permanent set is 2 meters times the residual strain. So it is 4 millimeters. Well, the result is the final length of the bar is 4 millimeter greater. So it is 2004 millimeters. Next, a brass bar has a length of 2.25 and a square section 90 times 90. Is subjected to an axial load of 1500 kilonewton. Determine the volume change. Elastic modulus is given, Poisson's ratio is given. Here we have the numerical data, elastic modulus, Poisson's ratio, force, square, and the length. Let's calculate the initial volume, L times B square, that's 90 square, L is in millimeters. This is the result. Now calculate the stress and strain. Force is newtons, that's 1500 kilonewtons, divided by square, 90 times 90 gives you 185 megapascals. Newton per square millimeters is a megapascal. Epsilon in the Hooke's law relation, sigma over E, and you know that E is 110 gigapascal or megapascal. So if you use both in the same unit, you will get a dimensionless strain value. These two values are the stress and the strain in loaded condition. Next, we have to calculate the lateral strain. So it is elongated. So the dimension 90 will get smaller. How much? The lateral is nu times epsilon longitudinal. That is 0.34 times epsilon. This epsilon was 1.646 times 10 to the minus 3. So if you do this calculation, you find the lateral strain is 5.7. Next, now I can calculate the change in the dimension. That was 90 millimeter, the square. This is the lateral. Delta B, the decrease in the dimensions of the cross section. The length was 2250. Longitudinal strain gives you the change in the length. So the new length will be this plus this. So it will be in millimeters 200. So 2.254 10 to the 3 millimeter. So the new width will be 90 minus delta B. That is less than 90. So we have the new dimensions. Next step is to calculate the final volume. What does it mean? The new length, the new width of the square. This is the final volume. Final volume minus the initial volume gives the volume change. Okay, that was the last problem. We have solved a couple problems dealing with the mechanical properties of materials. Thank you for listening.